Hello, 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 check, hello, 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 check, hello.
एवढा बारीक आवाज तर खाली होता, पण ते बोलताना काही लक्षात नाही आलं. एक काम करा ना, त्याच्यातला एक सध्याचा कट काढून ठेवून द्या, म्हणजे आवाज बंद राहील.
If this thing is working, normally yes. Which is quite close to the Devonian Carboniferous. This is the uppermost Devonian here. You can see that you have again an increase in extinction intensity. And again on this map of this Big Five extinction, you can see that there is some impact, but none of them are really coinciding with the mass extinction. This is generally a way after, post-dating. Some volcanic activity are possible, but not really proved. And here, again, sea level change, and again, the deposition of huge black shale, which are enriched in organic matter. And, well, what we will try now is to try to explain what are more or less the trigger of this huge mass extinction for the end of Devonian. But first of all, let me just trace a little bit the history of life between the end of Ordovician and the end Devonian, because quite a few things were happening during this time. And well, the first thing here, if you have again, we will move from around 443 million years up to 359 million years. That's to say the end of the Devonian. These are these two stages, two epochs, Silurian and Devonian. And you can see that they have been divided in many stages. I don't want to go in detail about that, but I just want to show you a little bit about the evolution of organisms, what are more or less the big events during this time. And first of all, one thing in the history of life which is quite important, around the base of the Silurian, around 440 million years, you have the first geofishes. Okay, meaning that you have geoless fish a little bit before, but these are really the first one which appear in the Silurian Sea. After that, very important things, and I think I was talking about revolution in life evolution, and I think this is really a revolution here. Again, what you see around 455 million years ago, you have, and here we have an extension of the screen, you have the first, you have the first, you have nothing, okay, okay, again it's here. Very important things, this is more or less the conquest of the continents of the terrestrial environment by the first plants, meaning first well-preserved plants with a vascularization system. Before that, I told you that the end of the Ordovician was characterized by maybe some kind of very primitive plants, but these are really the first one which are very well preserved, where we are really sure that vegetation was invading the terrestrial domain. Okay, and after another group which has been really powerful during millions and million years, were appearing. These are at the base, as you can see, of the Devonian, the first ammonoids. And these ammonoids are deriving from what I showed you yesterday for the Ordovician, this striped shell of the Nautilis were starting to coil and to evolve into an ammonoid shapes. Ammonites, I think you know what are ammonites. What are ammonites? They are cephalopods, so they are mollusks. And it's really interesting because they are, they disappeared at the Cretaceous-Tertiary boundary 66 million years ago. And so they were really more or less very, very abundant from the Devonian up to the Cretaceous. That's to say they really survive during almost 300 million years, which is really a lot. Why they survive? Because the strategy of life was really quite interesting. In fact, if you already have seen ammonites, I maybe have an example just a little bit later on. I will go back after to that. Okay. This is an ammonite here, okay? In position of life, in fact. This thing is the first ammonites you can see here. And these ammonites, well, derived from a stride form of a cephalopod, a nautilids, and start to coil. And inside these animals, you have several chambers. And the habitation chamber is the last one here. So the animals were living in the last chamber, and all the other one were more or less crossed by a siphuncle, which was distributing water and gas inside the empty chamber. So these animals was using a strategy a little bit like a submarine, if you want. And in the empty chamber, which are not really empty, this chamber was filled by a mixed between gas and water, which allows the animal to go down and up like a submarine in the oceanic water. And also, this was a locomotion way by just ejecting via a siphuncle water. This animal was able to swim. So it's actually this is ancestor, if you want, with a shell of some kind of calamar or things like that, calamari, for example, which don't have actually any more shells. But we have a survivor of a very close survivor to the ammonite. These are the nautilids, and nautilids are still alive. They are not very common, but they are living, for example, in the Pacific. And the strategy of life of these ammonites were quite interesting. So the animals was here. He was carnivorous, so he was hunting. And this was quite, let's say, strong predator. And these ammonites, during day, were living in the deep ocean, in the dark ocean, in order to escape to other predators. And during night, by this system of ballast, by this submarine system, they were able to go up to the surface, to go in shallow water, and to hunt little prey, or sometimes bigger prey. Because the size of these animals during the Cretaceous reached more than 2 meters in diameter, sometimes. Can be really, really big, okay? So these ammonites are very useful because they show a very high diversity, and they are really used for, let's say, the biostratigraphy. They are really nice. And for example, all the Jurassic and the Cretaceous biostratigraphy are based also on ammonite zonation. So the ammonites, for the first time, were appearing, the real ammonites, the coiled ammonites, were appearing somewhere in the base of the Devonian. So I will just go back now to what I was explaining. Okay, so we have the first preserved terrestrial plants, the first ammonoids, and something which is also very important, the first insect. And well, as you know, insect, especially for the flower plants, which appears later, very later during the Cretaceous, that's to say less than 100 million years ago, are very important for the pollination. And these first insects were invading the continental terrestrial domain somewhere in the middle Devonian, around 410 million years ago. No, sorry, 395 million years ago. And afterwards, a few after, you have what I call again really a revolution on the terrestrial domain. This is the appearance of true forest with big trees. This is the end of Devonian. And this will probably change a lot of things in any geochemical cycle, because for the first time you will form huge and deep soils. Due to the fact that you install vegetation, all these trees die one day, they form a lot of organic matter, and this organic matter contains very aggressive acid, which are able really to leach the rocks and to form what we call a soil, okay? And this soil is full of nutrients, and sometimes these soils can be remobilized and can be redistributed through rivers, lakes, down to the sea. And here you have plenty of nutrients which are very useful for all the biosphere. And especially the phosphorus is one of the main biolimitant nutrients, which is really very, very important for life, okay? We will talk probably tomorrow a little bit more about phosphorus as very important elements for life. Okay, and on top of that, another revolution in history of life, this is the first appearance of the amphibians. For the first time, more or less, as a boundary between the water and the continent is crossed by vertebrate. Before, you have trees, you have insects, but here, for the first time, the vertebrate are crossing more or less the boundary between the hydrosphere and the atmosphere. And for that, clearly, they change the way to breathe. And they got real pulmon, as we have, for example. Okay, these are the first amphibian, 365 million years ago. And a little bit, in the same time, almost, a little bit before, you have one of the big 5 mass extinction. We call that the Framanian mass extinction. It's very close to the boundary, or at its boundary, between the Franian. This is a stage which is taken from a locality in Belgium, and the same for the Framania. This is also a town close, section close to the town of Famen in Belgium. So you can see that Silurian and Devonian time are very important for the evolution. First insect, first forest, first amphibian. So this is a key period also. And on top of that, at the end, marking almost the boundary between the Devonian and Carboniferous, you have this mass extinction event. Okay, and this mass extinction event is followed quite quickly, especially at the beginning of the Carboniferous, by some glaciation. And here, this is not a small one. These are the huge Gondwana glaciation, which were occupying really an area which was really, really large. You can find glacial sediments in Africa, in South America, almost everywhere during this time. As you will see, I will show you that on a paleogeographical map. Okay, so this was more or less this Silurian Devonian time. And clearly we have also more or less some orogenic phases, like the Akkadian and Caledonian one, which is mainly a story during the Devonian. And the end of the Devonian is marked by the beginning also of the Hercynian orogenesis, which is a very, very important one, at least in Europe. Okay, about sea level fluctuation. Sea level fluctuation, we already talked about sea level fluctuation yesterday. And here, I don't think that you have that slide. I just had it last evening because I think it was maybe necessary. This is evolution, paleogeographic evolution. You have some paleomap here, which, if this thing is working, yes. And this is the Silurian Devonian. So you can see that, as we said yesterday, since the Cambrian up to the middle upper Ordovician, you have really a sea level increase, a huge transgression. And starting, sea level remain quite high in Silurian, but you have a huge regression, sea level drop, which will culminate here during the Carboniferous and the Triassic. Okay, so this means that this is still, so sea level is quite high during the Silurian, but becomes lower and lower during the Devonian. And this is mainly due to the fact that, well, you have here the situation in the middle Ordovician. This is the Gondwana. This is Laurentia, corresponding partly to Canada, USA. This is more or less a continent for North Europe. And you can see here that there is some collision leading to some mountain chains, the Acadian one. And what you can see that during the Silurian, the early Devonian, there is some kind of collision here. But the main tendency here is a huge regression leading to the formation of a huge, big continent here, the Pangaea. And this Pangaea will last during all the Triassic, Permian, and Trias. And this is quite important for history of life, because you can see that during the Devonian and Middle Silurian, you have a lot of continents, subcontinents, a lot of ecological niches, deep water habitat, shallow water habitat, continental habitat. And here you will see that this is for the Carboniferous, but this is still more pronounced for the Permian Trias. You will see that we arrive to one single huge mega continent. The name is Pangaea. So again, small sum up of what we just explained. You have here more or less situation in the Silurian, and you can see here that well, Silurian was a time of radiation for the mollusk, for the brachiopods, and for the first jewelfish, as I said. And well, we have the very early plants on land. And in the Devonian, this is the famous first ammonites. We have the first insect, and especially we have the first seed plants and the first forest here. And, well, as I said, the Devonian was really a time of the explosion of the fish families. A lot of fish were appearing here. We'll talk a bit more in detail later on. And the first amphibian that you have here is Ichthyostega, which is one of these key, let's say, animals showing more or less a transition between fish and amphibians, real amphibians, I would say. And these are this mass extinction occurring in the late Devonian. And the top of the Devonian, beginning of Carboniferous, will be marked by probably a huge ice age, as I said. Okay, so this is the late Devonian paleogeography, around more or less period where we have this mass extinction. These are more or less continent, and you can see here that we have already more or less some kind of aggregation of the subcontinent, which will go on during the Carboniferous and the Triassic. And well, the Gondwana was here. I put Morocco here because we will talk a little bit more in detail of a section located here that we have studied together with students. And you have two oceanic domains, the Paleotethys and the Rheas Ocean, which will be closed quite soon, as you will see. Okay, so by now, just a view of what was the Devonian in terms of marine life. This is there is an expansion, diversification of marine life during the Silurian and the Ordovician, but going on is Silurian, with a lot of brachiopods, coral reef expansion, a lot of coral, Nautiloids coining, giving rise to the ammonites, fish proliferation, some trilobites, graptolites, conodons, tomatopores, corals, and so on. All these guys, I can say that, were in quite good shape. And especially during this time, there was a very significant radiation of crinoids. And remember, crinoids are belonging to the phylum of echinoderms. They have some here some root stem, and here some branch which were agitating the water, and this is a suspension feeder, a little bit like irregular echinids of the modern time. And here you have a view of two kinds of corals which were very, very abundant during this time. Some colonial one, these are the Favosites tabulata, and these are some colonial, some solitary ones, the Rugosa. And these were forming a huge, really huge reef during the Devonian time. And they were completely decimated during the mass extinction occurring at the end of the Devonian. There is also nice animals here, which is an orthoceras. It's more or less a non-coiled nautiloids. And these guys give rise during the evolution to the ammonites. But this time was also a golden time, if I can say that, for the brachiopods. And there is really many brachiopods. Brachiopods are not mollusks, if you remember what I said yesterday, because they are quite different, because the brachiopods have a bilateral symmetry, as you can see here or here, for example. And they have this also suspension feeder, so they are filtering water, and generally they lie on the seafloor, and they are not really mobile. And some are really big, like, for example, this family here, the Spiriferida, which was very, very developed during the Silurian Devonian, could reach size like that. So they are quite big, okay? And actually, there is not so many brachiopods surviving. The Paleozoic, all this time, was really a time, golden time for these animals. And actually, we have, in fact, only two families which are surviving. This is Rhynchonelida and the Terebratulidae here. This is the two ones that we can find actually. All the other one, mainly, as you can see, got extinct at the Permian-Triassic huge mass extinction. So I say also that it was really a golden time for the fish diversification, and this is really true, as you can see here. You can see that we have, during the Silurian Devonian, more or less originating from jellyfish, we have jawfish, and we have many kind of fish arriving, and essentially the placoderm, and from probably these armored fish, which were, as you will see, quite terrific, big ones, big guys. Probably we get the sharks, the rays, and this is also, all these fishes here are clearly more mobile and faster than, for example, the placoderm. What about the placoderm? I have nice pictures here. They looks not very sympathetic, I have to say. They were very big. You can see that more or less the skull of these guys, which is an armored fish, was something like 1 meter. And well, they appeared at the beginning of the Devonian, but they disappeared quite quickly at the end of the Devonian, and maybe the beginning of the Carboniferous. And it's believed that the cartilaginous skeleton of sharks and ray are deriving from these guys, okay? So huge time of proliferation, diversification, for the fish. And what about the ammonites? We already talked about the ammonites, and here there is maybe a better picture. So this is an illustration of the coiling of the ammonite during, let's say, Ordovician time. So what you get here, it's a really right shape, and the siphuncle of this Orthoceras was located in the middle and crossing all the chamber. And you can see here that you can see this coiling leading to this ammonite forms, which is quite close than the nautilid forms. This is one of these right nautilids, which evolved into this coiled ammonite. And here, what you can see on this very nice goniatite from the Upper Devonian, you see this more or less boundary here at delimitating the chamber. And this chamber are crossed by siphuncle, which more or less was distributing mainly water and gas into this chamber. And this gas and water was very useful in order that when the animals was going down into the sea, more or less to compensate the pressure, but also as a locomotion mean. By ejection of this water, it was able to really move very quickly, and the ammonite was moving from behind like that. And these are like the nautilids. And this is quite important because this explains that ammonites and nautilids actually have really some kind of what we can call a modern eyes. Big eyes, a little bit like the horses, if you want, and this eyes was so big that the animals was able almost to look behind because it was moving from the back, okay? Some of these ammonites, and especially another group, the belemnite, which are the ancestor of the calamar, were able to reach very fast speed. Some acceleration by ejection of water. Some people did some modeling. The belemnite, for example, was able to attack a prey at more than 60-65 kilometers by hour. This is just an acceleration. And these were really quite predators, very carnivorous animals. Another thing which is very important, and probably more important, as I said, this is conquest of the continent by plants and animals. And well, if you go onto the continent before, let's say, during the Cambrian Ordovician and partly Silurian, probably you have lichens, microbes, algae, which were formed in the terrestrial environment. Not so much. But since the Silurian, and especially in the Devonian, we have the first vascular plant, meaning that they have a stem here, which with a tube, which allows transport of water nutrients from the roots to the plants, which is clearly a revolution. And these are more or less the landscape that we may have during the Silurian. And this landscape was made by these plants. And during the Devonian, we got the installation of the first big forest. So this is a revolution, especially in terms of oxygen, because, as you said, we said yesterday, trees, plants are doing photosynthesis. So they are providing oxygen to a lot more oxygen to the atmosphere. And you will see later on, and I will explain this probably this afternoon, that during the Carboniferous there was so many forests and trees and plants on land. They provide so much oxygen to the atmosphere that they draw down the CO2 and they provoke a huge cooling, leading to this huge Gondwanian glaciation, ice age from the Gondwana. Okay, So this is really important in terms of climate, but also, as I said, this is the first really time where we form huge soils. So it will completely transform the cycle, because it means that you jump from a weathering which is mainly characterized by the physical erosion, for example, by the wind or by ice. So you grind the rocks, to a chemical weathering. So you dissolve, if it's a simplification, clearly, you dissolve the rocks. But this is very important. Why? Because when you dissolve the rocks, you have a lot of nutrients which are available. And if you increase the greenhouse condition, if you increase the rain, you have more and more alteration. And I remember you that during this alteration, you transform the minerals from the crust, like the feldspar, into some clay minerals or things like that. And in order to do that, you will take or uptake to the atmosphere 2 molecules of CO2, okay? And when you precipitate into the sea, when an animal is building its shell, he will use only 1 molecule. It will reject 1 molecule to the sea and atmosphere, but you will have the sequestration of 1 molecule of CO2. So it means that this new system allows really to have new geochemical cycles, okay? For example, you know from where is coming the phosphorus? From? It's from the crust. You have some minerals, for example, in some igneous rocks, like granite, which have a lot of apatite. And apatite are minerals which are mainly have phosphorus, okay? And if you increase the leaching, if you increase the chemical leaching, the weathering, you will get more and more phosphorus into the sea. And you will boost the productivity, for example. So all these things are very important. They are partly links to the presence of trees and soils on land. And this is another revolution, clearly. So the next big step into the evolution, this is that. This is in fact the appearance from of the first amphibian. And this Ichthyosega is more or less the missing link. This is this guy here. This is the missing link between the fish and the amphibians, okay? So you can see that we have gradually the transformation of a fish state to an amphibious state, a real one, which is appearing really during the lower Permian. This is very important because from where you will get anything, mammals, dinosaurs, reptiles, all these things, okay? So this is quite important. And Ichthyosega is very well known because this is a missing link between the fish and the amphibian. Do you know another missing link? Between, for example, 2 big family. What? So, do you know what is an Archaeopteryx? Okay, what is an Archaeopteryx? Yes, Archaeopteryx, this is really the missing link between the dinosaur and the birds, okay? And this Archaeopteryx has been found in one place in Germany called Solnhofen, where the preservation of the fossil are really excellent. And this is clearly the missing link. That's why when people say that all the dinosaurs got extinct, this is not completely true. The big animals were extinct, but not whole, because birds are more or less originating from dinosaur groups. Okay? Okay, now let's try to see a little bit what happens during the end of the Devonian in terms of mass extinction. So this is that one here, as you can see here. This is the top of the Devonian. And, well, yeah, this is a view of a section where you can see the presence of laminated black shell, which are interrupting a sedimentation which is made of carbonate very rich in ammonites. This is an example that I will show you in details in Morocco. And if we take the biodiversity during the Phanerozoic, this mass extinction is just here, okay? This is FF, Framien mass extinction. Okay, so in fact, the end of the Devonian was marked by, in fact, 3 extinction events. If you take the percent of extinction here, and this is the stage of the upper Devonian, you can see here that we have these events here. Taganic, we have the Kelvasser, which is a bigger event, and we have the Hungenberg. And in fact, this huge mass extinction is made of threefold mass extinction. And here there is some difference between, s'il vous plaît. Okay, so we will see that in more details. You have the Taganic event, the Kelvasser event, which was the biggest one, and the Hungenberg event, which was also the biggest one. The Devonian, so, is marked by several crises, as I said. The late Devonian is also characterized by a global sea level rise, as you can see here, beside transgression up to here. You can also see that we have some variation in oxygen isotopes. And for example, this Kelvasser event, these 2 black shells are marked by increasing temperature. I will go back to that later on. But it means here that the late Devonian, this is not one single extinction. In fact, this is a combination of 3 extinctions. And this cartoon is illustrating quite well what I want to say here. This event here, which is marked by what we name the Taganic event, and you can see that there is here, in terms of biodiversity, especially of the benthic fauna, brachiopods are less diversified, bryozoans are almost disappearing, and the corals are starting to suffer. Trilobites, nothing really serious, but the corals are mainly the group that will be the most affected during this time. So this was the first event. The second event is corresponding to the Kelvasser event. I will go back to the more or less Kelvasser. It's a section in Germany, and you can see here that brachiopods really have a loss of diversity. Nothing happened with the bryozoan, but corals, mainly the colonial and the solitary, Rugosa and Tabulata, were really almost extinct. And this is not surprising because, as you know, the reef are very, very, very sensitive ecosystem, and we actually, with the warming of the ocean that we have, the actual warming, some of the best, the most beautiful coral reef are gently disappearing. I'm talking, for example, of the coral reef from the Bahamas, the Red Sea, or the Great Barrier in Australia. Why? For 2 reasons. We'll see this in more details, but first of all, increasing sea level. Why? Because as one people say yesterday, you have a melting of the ice, so sea level is increasing, and normally, if a reef is in a good shape, it will just follow the sea level and move with the decrease or increase of sea level, what we call generally a downstepping or the backstepping of the corals that you can really follow. But for that, you need a coral reef in very good shape. So this coral reef has to be in good shape. It's not the case, actually. Because actually, what we have a transgression, but also warm and warm and warmer water. And more or less, the interval where a reef can really develop in terms of the temperature of the water is very, very small. It's in between, for the big coral reef, between 26, 28, 27, 29. Over 29, the coral reef will bleach and die. And another thing which is quite important, we have also more and more and more human activity close to this coral reef. So what does it mean? It just means that coral reef, you know, it's photosynthetic animals. In fact, the corals have a symbiotic algae which help us to produce calcium carbonate in order to form the skeleton. And there is a huge photosynthetic activity. To have this activity, you need clear water, blue water, without suspension. With human activity, with the increasing greenhouse effect, you get more and more nutrients, suspension into the water, and this is clearly lethal for the coral reef. So what happens today in very quickly has happened during, as you will see, this Devonian time, okay? And the next event is also quite marked in terms of biodiversity. You can see here that, well, some stromatoporids, which are colonial, let's say, like reef, are disappearing. Trilobite, vis-a-vis arthropod, were suffering a lot during this event, but a lot more here. And mainly, again, the benthic fauna is quite suffering. What about the nectonic fauna? Some nectonic fauna, these are the swimmer. And the swimmer, well, have clearly some decreased biodiversity. And you can see here this famous placoderm armored fish, which were really in danger during that phase, completely disappeared in the last phase of the master third of the big phase extinction that you have here. And the ammonites also are more or less suffering a lot. Conodont, which are linked to some very primitive chordates or chordates living into the water, the ancestor of the fish, are also suffering. And this just means that especially this last phase here, this one, in fact, especially that one, was quite, let's say, lethal for all the nectonic fauna. So during this threefold phase extinction, you can see that 2 or 3 times the benthic and the nectonic fauna were affected. So we can abstract that on that diagram here. You can see here that, in fact, the let's say Middle Devonian extinction, Taganic extinction, was characterized by the decline of a long-term diversity. But the most severe crisis, this is linked to these 2 events. But the name is Kellwasser, and Kellwasser, it's the name of a place in Germany. And these Kellwasser are marked by 2 transgressions. I will explain this in more details now. But this is clearly the big mass extinction. And this is the most severe because, well, you don't have a lot of reefs surviving and so on. And the next one here This was the Langenberg extinction, mainly affected pelagic groups or nectonic groups like ammonites and fishes. Okay, so a threefold mass extinction. Okay, so now I just want to explain a little bit in more details the mechanism of, if I just go back for why, of, let's say, that one, the main one. And this one is very particular. I have to say that we don't have all the answer because it's a quite complicated mechanism, as you will see. And I will try to explain you by trying to remain very, very simple. Okay, what do we see? This is the Franian-Färmian boundary, and this thing I have to, sorry. Explain you this like that. Everybody's, yes, can show that. So this is Franian-Färmian, and here you can see that this part of the Devonian is quite well dated thanks to the conodonts. I remember you, the conodonts are very small jaws or very primitive chordate or hemichordate, the ancestor of the fish, which were very, very abundant in the Paleozoic seas. Okay, and these are all these names. The names are not very important, but just to know that we have a good idea about the timing. Okay, and here what we see, in fact, this is the presence of two levels of black shale. Do you remember what is black shale? What is black shale? A black shale is a finely laminated shale. We generally have almost no carbonate. Why? Because all the carbonate just disappear because there is no more production of carbonate, because there is almost no more organism able to produce carbonate. And the lamination means absence of biotubation. What does it mean if you don't have biotubation on the seafloor? Don't be shy. If you don't have biotubation on the seafloor, it means that you don't have life on the seafloor. So if you don't have life on the seafloor, what does it mean, for us at least? No oxygen. Oxygen depleted zone, anoxic condition, okay? How do you form anoxic condition? We'll go back to that tomorrow morning. I will explain you a little bit more what are black shell and what are anoxic condition. But it's very simple, in fact. Well, you have the water column. In the water column, you have some organisms which are living. And if you increase the nutrients, like phosphorus, you will boost the productivity, and you will get more and more and more organisms. And it's a little bit like if you take a lift and you have two people, there is no problem. But if you put 100 people in a lift, if the lift can still, well, support it, what will happen? You need oxygen. And if you have too many people in the same room, there is no more oxygen. So you will die. It's exactly what happens. A lot of these organisms are dying, going down to the seafloor. And what happens in the seafloor, which is already quite devoid in oxygen? In the seafloor, you have, by this way, a lot of organic matter. And here, what will happen, you have bacteria. And this bacteria will reduce this organic matter, and you will have still, they will use the oxygen to reduce the organic matter. These are the sulfate reductor bacteria. And what will happen, you have still less oxygen on the seafloor. And by this way, no life is possible. And we'll go back Friday to that problem, because this is a big problem for the actual ocean, because in the actual ocean we are forming a lot of what we need dead zone, place on the seafloor where life is not anymore possible. So you have here 2 episodes of black shell deposition, meaning that suddenly here, during a sea level rise, you have almost no life possible on the seafloor. But sometimes this oxygen minimum zone may not be only limited to the seafloor, but this oxygen minimum zone can grow and reach the surface of the ocean. That's why we name oxynia, okay? Meaning that all the ocean is under anoxic condition. And this was the case for the big mass extinction of the Permian-Triassic, where almost the global ocean in all the world was characterized by huge anoxic condition. And this may explain why during this time you got a so big extinction. It's not the case here, but here's the interesting things. You can see that we have 2 horizons, and these horizons are marked by some geochemical markers, isotopes that we use here. In fact, these isotopes are quite easy to understand. These are the delta C13 measured on some animals, carbonate shells, and you can see here that during this time they are increasing. They are quite stable, +1, increase to 3,4, increase to 3,4 here. What does it mean? It means that you increase the productivity. It means that you increase the transfer of organic carbon to the seafloor, because if this ratio is increasing, it's because the 12C has been used by the animals. So what remains is only the 13C. That's why you have a positive peak, okay? And it means generally that you have a huge organic matter deposition. And these things here, SST, this is in English the sea surface temperature. And here there is some interesting things that you can see, that you have warm here, followed by cold, warm, cold, warm. This is like a yo-yo, okay? And this is interesting because you can see here that you start first to increase the delta C13, a lot of organic matter, and gently, with a lag, you get a decrease in temperature, okay? Against warm, against cold. Why we do that? If you have a huge sequestration of organic carbon, what does it mean in terms of atmospheric CO2? What will happen globally? If you have a sequestration of the carbon in a black shell, so you will decrease the CO2 pressure, okay? The global CO2 pressure of the ocean atmosphere will decrease, and if you do that, what happens? You get, very simply, a cooling, because you have less greenhouse gas, you have less greenhouse warming, and you get a cooling, okay? But for the animals, you have to think that this kind of event, that's to say warm, low oxygen condition, cold, low oxygen high oxygen condition, warm, cold, this is not very good, okay, for life. And these things here is, you can see here, there is some biotic event, the decline of the reef, and the disappearance of a lot of animals, which are more or less characterized by mainly benthic animals, but not always, okay? So this is more or less what we see. And now, let's go in a little bit more details about the section. So where are these Kellwasser? They are all over the world. This is quite interesting to see that these 2 horizons of mass extinction, you can have it, for example, here, in very 2 separate places in the world. You can see it here in Tennessee, USA. This is the lower Kellwasser. So what you see here, it's clearly that you have carbonate, okay, with a lot of ammonites, reef, and so on, interrupted by the deposition of black shale. This black shale are laminated, and there is almost nothing in, okay? So meaning that this is the first extinction event. After on top, I will show you more details with an example taken in Morocco, again carbonate. And here you have the lower one and the upper one. This thing is in Germany, in Europe, but again, you can see black shell, laminated one, with almost no life in it. And if you go in Morocco, this is an overview of the upper black shell event, upper Kelvasser. So we name this Kelvasser because the place of these two black shell has been named is in the valley of Kelvasser in Germany. So here, this is upper Kelvasser level, and you can see some carbonates here, and here some black shell, laminated. There is almost no oxygen. A lot of organic matter in these things. And we have the chance also, very recently, as a paper that we published when we have postdoc students, which was working almost 2 years as a postdoc in Lausanne on this Devonian mass extinction. This is again in Germany. And here the good things that you have these two black shell events, and here you have the presence of a bentonite. What is a bentonite? You know? Clay minerals. This is fully right, but from volcanic ash, exactly. And you have a lot of them in India. And we'll go back to bentonites when we'll talk about Deccan also. Ash layers. And by chance, these ash layers here is just above the lower Kelvasser event. And in this ash layer have zircons. And for zircons, you can apply an isotopic system named uranium-lead and get very good dating. And the precision is, you can see it for quite old rocks like that. This is not so bad. This is the age. So by this way, we can have some good, more or less, age of this event. This is quite important, because we need absolute age in order to determine exactly the timing and the tempo of such events. More bentonite we have, better it is. So the error bar here is quite big. For example, in the Deccan trap zircons, that I will explain probably after tomorrow, the error bar is a lot less. It's something like in between 15 and 50,000 years. So you can really use it to have a very fine dating of, for example, the volcanic activity of Deccan traps. But here, this is quite more complicated. But the chains here, and in geology, you must have some chains sometimes. This bentonite is just in between these two Kelvasser events. And these are very new results that we just published. Okay, so in terms of stabilized isotopes, I tell you here that we have the proof of a sequestration of huge quantity of organic matter if you look to the delta C13 here. So because you have this huge increase in delta C13, meaning that you have quite a lot of huge, strong productivity corresponding to the 2 Kelvasser event, and these things here, you can see he is followed slightly, with a slightly lag, by some oxygen minimum, oxygen isotopes showing an increase, so cooling. Okay, so the starting point here of this sequestration of organic matter is marked by warm condition, and after, when you increase the sequestration of the carbon, you will get cooler conditions due to the sequestration and drawdown of CO2 into the atmosphere. You know, all these things are very important because it helps us really to understand what happened actually. Because actually we are doing exactly the same thing. You are, by the use of the fossil energy, you are putting more and more and more greenhouse gases into the atmosphere. And this is very useful to look into the past, to learn from the past. And to me, the men are forgetting a lot history. You know, they are doing always the same error. Even if we know that all these things are bad, we are doing this anyway. So we have to learn from the past. And the interesting things that you have 2 times the same things. Warming, cooling, okay? And for the animals, this was clearly not so good. Okay, how to explain that? Well, I have to say it's not so easy because there is this double things, this double occurrence of black shale. And what we know that at the beginning we have in the Franian warm condition. Warm condition in terms of oceanography means stagnant ocean, no dynamic current. So if you do that, you will create probably, and especially on a transgression, this is the water is moving to the shelf and will recycle a lot of nutrient. You will get more nutrient in a stagnant ocean, you will get anoxic condition, okay? This is a little bit like the Black Sea model. I will go back tomorrow about that. And first of all, you have these things. And these things can be also amplified by some upwelling of deeper water with nutrients and rich water. So you get high productivity, anoxic, and organic matter deposition. This is the first black shale deposition, the lower Kevasser event, okay? And afterwards, you will get high productivity. So you will have a carbon sequestration. This carbon sequestration will lead to a decrease in the PCO2, okay? If you do that, what happens? You draw down CO2, you decrease the temperature, you get a cooling. If you get a cooling, it could be maybe possible, and there is some proof, at least in Africa, that you get a cooling, you get some ice, glaciation. And what happens if you get some ice? You get a regression, sea level drop, okay? And this sea level drop, what will happen? If you get cool waters, sea level drop, you have a more dynamic condition. So you will go from anoxic condition to disoxic, anoxic condition. And this corresponds to the middle part between the 2 black shale events. And after, you get, again, if you have more and more, let's say, opening activity, maybe, you get probably some nutrients going into the water, again a transgression, again a warming, and this is clearly this kind of system, feedback loops, which are working, and which are not very good, clearly, for the organism. And the delta C13 is proving that, because you have this variation, you increase the delta C13, and after you decrease the delta C13. Okay, so, oh, I forgot to translate this title, sorry, but you learn French a little bit, it's good for you. Extinction massive du tardi Devonien means massive extinction of the late Devonians. Very easy, no? And interpretation, it's interpretation. Okay, so, okay, why do we have so much nutrients into the sea occurring suddenly or at the end of the Devonian? And here, this is a working hypothesis of a group, and this is a nice paper from Algeo et al. 95, where he linked more or less this extinction with the appearance of terrestrial plants and forests, which is really interesting. And what he said, okay, we have increased chemical weathering because you have soils. And if you have soils, you have plants. It means that into the soils you have a lot of acidity which will weather the rock bed as bedrocks and deliver a lot of nutrients into the soils. And if you have sea level transgression coming into the continent, these soils will be, these paleosoils, remobilized, and all the nutrients will go into the water, into the sea again. So you boost the productivity, okay? More nutrient, mainly phosphorus. And after, okay, you get the black shell deposition, the anoxic condition, okay? You increase organic matter, you increase the oxygen depletion, and you get the anoxic condition, okay? And at the end, if you do that, you have a CO2 carbon sequestration. What we really are trying to do, actually, if we can find a way, as the Earth is doing, it would be very nice. Because now, if you increase the black shell deposition, you have organic matter sequestration into sediments, so you have a CO2 decrease and a cooling, okay? It's exactly what we don't have. That's why a lot of people are thinking, actually, to have a CO2 sequestration into rocks, for example. To take, for example, all the CO2 that are using by the burning of charcoal, like in India, and to re-inject the CO2 into the more or less subsurface. It's not an easy task, but people are doing that, actually, in Switzerland, for example. It works, but sometimes it may provoke some collateral damage, like earthquakes. So we have to be a bit careful with that, especially in Switzerland, where you have a small town almost everywhere. So it's not evident to find a place where nobody is living, and in order to avoid this kind of problems. But look, this is quite important. Earth, the biosphere, has some kind of auto-regulation, meaning that in case of a problem like that, she is able to have this auto-regulation, self-regulation of the problems. But this self-regulation, which is natural, we have no humans during this time, clearly, take times, okay? And that's why this is a big difference with what we will see Friday with the discussion about the Anthropocene. Okay, so this leads to double extinction, if you want. So, in fact, what I like to call this mass extinction from the Devonian, this is what I call the greenhouse yo-yo effect. You get warming, a transgression, a shelf-drowning, paleosoil remobilization, nutrient remobilization. So you have organic matter sequestration into black shell, and after you get clearly a drawdown of the CO2, glaciation, regression. And when you have a regression, which is also quite important, you will also have the exposition erosion and the oxidation of this black shell. And what happens if you have an oxidation of the black shell? What do you produce? CO2. Oops, not water, CO2. CO2, exactly. This is also a source. The CO2 may increase again, and again, you start again these things. The problems here is we don't really know why this feedback loop were not acting forever, because you can say, okay, it could be. And here I think it's mainly a question of probably sea level, paleogeography. There is other parameters which are acting. And this is, I remember you, one hypothesis. A lot of people, it's quite controversial, but I think it's really a nice way to explain why we have this kind of change on Earth's surface. And this is a very nice example of the self-regulation of the Earth. I don't know if you know this book, and I would recommend you. to read it. It's a quite nice book by James Lovelock, The Gaia Hypothesis. Lovelock is thinking, it was the first really at least to write something like that. We know that there is this kind of self-regulation of the Earth via feedback loops, but this was the first to really show how the Earth was able to recover by itself. The self-regulation of the Earth. By now, well, this self-regulation took million years. Well, let's say sometime less, but at least long duration. And well, the auto-regulation with the actual warming, this is something which is probably, unfortunately, not possible. And here, we will go on through the Earth history, and we will enter in the Carboniferous. And really like this kind of cartoon here by Algeo, where you is not okay. I have to charge this thing more, but anyway, this is interesting. You see more or less this is a arrival of the vegetation. Let's say in the Ordovician, and after into the Devonian. And you can see that you have more and more trees, and the roots are more and more deep, more and more active, and you get more and more thick part of the soil which are affected by this phenomenon of weathering. And it's really, I guess, that this decrease in atmospheric CO2 is really linked to the arrival of trees on the continent. So you have, if you have trees, I say, you have an higher photosynthesis rate, and what will happen? You get more oxygen into the atmosphere. And but you have also the accumulation and preservation of wood under coal deposition. So you have a sequestration of carbon and CO2, okay? And so this leads to a huge cooling. And this is next presentation. So, okay. So we have time. We have still some times to go. Yeah, half an hour before lunch, and I will start to explain you what happened during the Carboniferous. If I can. This is chapter 3, and here I have to say that I had a little bit more slides than you have. I will tell you which ones, because I think that there is a few things which were quite important to add. So I did this yesterday evening, but it's not so many. But I had a little bit more about the Carboniferous, between, I think it's a quite important period. I don't know, I have a question for you, for the geologists. Do we have Carboniferous coal in India? We have lignite from the Paleocene, Eocene. So I never know with you, this is no or this is yes. Because in Europe, you know, if you do that, I'm doing very badly, sorry. But it means no. If you do that, it means yes. So I am several times very confused. So you say no. That's right? Yes? No, it's really funny because for us it's very complicated. And sometimes, well, it's the first time that I was in India, I was asking my way for an hotel. And each time it was like that. So I said to the taxi driver, it's not here. You just to go on. And we were circling around the hotel for at least 2 hours. At the end, well, the guy was saying, no. I said, oh, it's no. Okay. Well, so for me, sorry. If you say that, maybe I will not react. Because we are not used to that. It's exactly, in Europe, it's exactly the contrary. This is quite funny. But anyway, I am used by now, because each time that I asking to say something, and he say, yeah, well, the first day I had to say, did he say yes or not? But by now, I know. So there is no Carboniferous in India? This is my question. I don't know, huh? It's a question. Yes? Yes or not? You can say yes or not. It's more simple. Yeah. No? Okay. Because you have a huge quantity of coals in India, which are linked to what? What event? But we will see also in detail. So I will show you a lot of pictures of lignite mine, first there probably, from the PTM, Paleocene-Eocene boundary. And here we talk about a rather controversial topic. This is the origin of the mammals, modern mammals, which are linked to this PTM. But anyway, we are not there. We have still quite some travel to do, because, well, we have a few million years to cross. And now let me talk before the break a little bit about what happens before this Permian-Triassic mass extinction. This mass extinction was the biggest, the largest that we know. Almost 96% of the species were disappearing. 96%. This is almost everything. And at least in the marine domain. We don't know so much about the continental domain. 96%, this is really a lot. And you have to think that, for example, the corals, the reef, were disappearing during this time. And they were reappearing only a few million years after. It took for the corals just to reappear, and it was not exactly the same phylum, in addition, and to more or less be again into the Triassic Sea, it's a question of almost a few million years. So it was probably a period which was really hard for life. And in Lausanne, we have a whole group working also on this mass extinction. I know that in India you have some Permian. I am right. Yes or not? You have some Permian in India. I know that there is also some Permian in Pakistan, but I think in India also there is some Permian. But I would, excuse me? Eastern Asia, yeah, sure. But in India, you know where? Yeah, I don't know. It's something which I'm not very used to, the Paleozoic in India. Okay, so, but before that, and before the lunch, I have still 20 minutes, so let's talk a little bit what happens before the Permian-Triassic. Because, as I said, if you want to understand what is really a mass extinction, you will need to see what you have before and what happens, let's say, in a few millions years before. So, again, this is the Carboniferous Permian period. You can see that it's quite a long period, almost 100 million years. And, well, the Carboniferous, as the name is indicating, is time of the plants, huge forest everywhere almost, and very low CO2 content. And in fact, during the Carboniferous, there was probably more oxygen than actually. Meaning that, for example, the condition for the insect, because there was no bird at this time, in order to fly was a little bit difficult, because, well, the space is lighter, and that's why you will see, I will show you, some dragonfly, huge one. You have to think that they had almost 70 centimeters space for the flights, like that, really big animals. And they did that in order to adapt to this rich oxygen condition. So it's a view of the forest, and let's go. You have a radiation phase right starting after the mass extinction of the end of the Devonian, and what you get here during this Carboniferous time. This is the first reptiles. So this was the time where the ancestor of the dinosaur, but also of the mammals, us, were coming in, okay? You have the first amphibians in the Devonian, and after you have the first reptiles, and after you have, something which is quite important at the end of the Carboniferous, more or less, the first gymnosperm, seeds, plants. And this is also very important because this means that you have the first seed plants and the angiosperm. So the gymnosperm are the fern plants, okay? And the angiosperm of the flower plants are arriving a lot later in the Cretaceous, meaning almost, let's say, 150 million years later, okay? But this is quite important. And during all this time, you can see here that you have a huge, huge glaciation. This is a ice age from the Gondwana. Everybody knows about the Gondwana, which were covered by a huge glacial during this period. And on the same time, you have also, and this is also quite important, some a huge orogeny named Hercynian, which concern main part of Europe, but also later on USA with the Appalachian. Okay, so this is more or less the story. And here, the cartoon that I like to show of Stanley, it's really, no, it's not, I was thinking that it was on screen, okay. Showing more or less what happens during these two periods. I really like that books because there is a lot of illustration. I can give you after a list of reference. I just forget it. I will do it, and Syed, you can print it because there is this book is excellent about Earth system model. Okay. Carboniferous, as I said, you can see here that the starting point of the Carboniferous, you have a radiation in ammonites. Here you have a nice ammonite in life position, okay, a little bit like the actual nautilids. You have also some crinoids, your gastropods, corals. Life in the ocean was quite good during that. Life on land, we don't really know, but there was clearly a lot of trees, but the insects were appearing. And in somewhere in the late Carboniferous, you have some extinction again, and proliferation of amphibians, and the appearance of insects with fixed wings, and this huge, huge dragonfly. I will go back to that for the late Carboniferous. And very important, you have the early reptiles here with the first therapsid here, which lead after, as you will see, to the dinosaur. What about the paleogeography? Okay, the paleogeography is very important for the Permian-Triassic crisis. You can see that, again, we have seen this sea level transgression during the Cambrian-Ordovician Silurian. The starting point of regression into the Devonian, and the regression is just going on with a maximum at the Permian-Triassic condition. And here, this is a continent location during this time from early Carboniferous. And what you can see, that in the early Carboniferous, we have the closing of this ocean and a collision here between Africa and this Euro-America, leading to a huge continent in the late Permian, okay? And this is a very important thing. And this is linked to the Hercynian orogeny. So this was a period of collision, and uplift of some mountains. But at the end, you have quite a huge, unique, single continent named Gondwana. And this is important. Why? Because it just means that first in terms of climate, this kind of unique continent are quite sensitive to climate change. And you will see that at the end of the Permian, you will have a lot of aridification. And the Permian time is the deposition of huge evaporite. You know what is evaporite? Sediments. What? Excuse me? You have to speak loudly. Yeah? Yeah, yeah. So what are the minerals that you find in evaporite? Alite with salt, in fact, NaCl, and also gypsum. Okay, and anhydrite. And in fact, you are right. You can have this in a lake or in an internal sea. If you increase the temperature, you increase evaporation, and the balance between precipitation and evaporation becomes negative, and you increase evaporation, and you precipitate all these minerals, which are alite, anhydrite, gypsum, and some more different salt. And this is a chemical precipitation, okay? There is no organism which are involved in this kind of precipitation, contrary to the precipitation of calcium carbonate, which are biologically induced, okay? And this is really linked to a huge acidification during this time. So, and this is due to the fact, to this very particular organization of this Pangaea, this is the name of this continent. By chance, in order to understand this mass extinction, we have still, for example, in China, some good outcrops in marine condition, and in Greenland, as you will see also. How was life during the Carboniferous? Okay, first in life in the sea. So after the end mass extinction of the Devonian, you have a huge ammonite diversification and proliferation, brachiopods, bryozoan, crinoids, well, very diverse. But one important thing that you maybe know, or maybe not know, this is the first appearance of this very large benthic foramifera named Fusilinids. Okay, and this is a thin section view, and this can be large like that. And just think, this is one single cell. One single cell is producing an organism with a wall, as you can see, and perforation here, which can be big as that, one cell. And in order to precipitate so much calcium carbonate, clearly there was a symbiotic algae, which was helping these animals to produce this calcium carbonate. These are generally green algae. And for that, it means that if you want to have a lot of fusilinids in the sea, you need olidotrophic condition because you need light for the photosynthesis, okay? And these fusilinids are living generally in association with coral reef. So just think coral reef, very nice blue sea, like on the postal card for your holidays. And when you see a crinoid, this is black, brown waters, horrible waters, which are full of suspension, okay? Just think about that, it's very important. Mesotrophic condition. And we have these placoderms, armor fishes are disappearing, as I said, and they are replaced by more mobile fishes and faster fish like sharks or rays, okay? This is also an evolution. What happens on Earth? On Earth, this is really the time of the forest, as I said. That's why we name that period Carboniferous. And well, during the Carboniferous, In the Devonian, you have the first small spore plants, and after you developed the ferns and the seed ferns, and at the end also the conifer are appearing at the end of the Carboniferous, and but the dominant were lycopods. All these sphenopsid, lycopods, and the third ferns were forming huge forests and delivering a lot of oxygen into the atmosphere. And this is a view of that period on the continent. So we have a huge forest, and all main part of the coal reserve from the world are coming, not in India, but in France, in Europe, in Germany, in US, are coming from the Carboniferous plants, okay? So meaning that you get a lot more oxygen, and there was more oxygen during this period than now, and extend this forest, and we have larger insects like this dragonfly with a wingspan of 70 centimeters, for example. You have a reconstitution here, and we think that these things was an adaptation of the excess of the oxygen, and adaptation to the fact that they have to fly in a space which were more lighter, okay? It's more difficult to fly. So it's probably an adaptation. But this is really huge dragonfly, okay? And, okay, we have more and more oxygen into the atmosphere, and we have some curve here. For example, these curves show the percent of oxygen into growing here, as you can see here. This is the time of the Carboniferous, and this is the depletion of the CO2. And well, you can see that this period was really, really enriched in oxygen due to the proliferation of the forest and the trees, and the more or less stronger photosynthesis activity. And you can see here that we have clearly a cooling event which will occur, and I will finish with that. Just a map here to show you where are the non-carbon accumulation during this time. As I said, you have a lot here in USA. This coal has been deposited in small basin in Australia, and clearly, well, here in Europe, but not also that we have a huge deposition here in Siberia. This is very important to understand the largest mass extinction that the world have known since the beginning of the Cambrian, because this huge coal accumulation has been caused by volcanism. And in the coal you have what? A lot of CO2, a lot of sulfur, a lot of mercury, a lot of lethal things which will enrich the atmosphere during this time. From that drawing, apparently there is some coals here in India. But it's not very interesting for us. Why? Because this coal is not located where the Deccan is. So the Deccan probably never cross these things, maybe with an exception of the Narmada Rift. We are working actually on that. Now, so if you accumulate this coal, you do a huge carbon sequestration, and you get this cooling event. And I think that everybody learned about the Gondwana glaciation. And here, for example, this is a view in South Africa of strike, which are mainly due to the glacial, okay, during very polished rocks, and led some strikes. It's clearly a mark of a glaciation. And here you have some warped sediments in a periglacial lakes. And you can see here these small blocks, it's a dropstone. I tell you the drop stone are linked to the fact that iceberg, which are produced on an ice sheet, at the base of the iceberg, you scratch the rocks and you incorporate blocks at the base of the iceberg. And after this iceberg is delivered to the sea, is melting, traveling, melting, and from time to time, one of the stone is dropping into the sediments. And you can see that generally the sediment is deformed, showing that it happens during this time. These varve sediments here are linked to season. Okay, these are generally periglacial lakes, which lakes located close to glacial. And well, what happens that at the end of the winter, you melt, you have a lot more water runoff, so you will put some sand. And this clearly darker, more things which are a little bit coarser, a little bit browner are sand, links to generally the end of the winter. And the light one may be linked to the production of the lake, like the diatomites, things like that. Not in this time, because diatomite are appearing in the Cretaceous, but it must be some other organism. But these are seasonal. This is wonderful. You know what? You can count here the years. This is an incredible preservation of the time. Okay, and you can see that this ice sheet was located here on different continents, including Australia, including part of India. I don't know where in India we can see that. Maybe not anymore. It's maybe covered by the Deccan, and also more sediments, but also in Africa. So this was a huge one, a huge glaciation and a huge cooling. What is the model about that? Again, it's a little bit the same as I said for the Devonian, the end Devonian. Well, you have first the Hercynian orogenesis, some increased weathering, first of all, and especially you have this huge forest and some deposits of carbon leading to CO2 sequestration. So the CO2 will decrease and you will get cooling and a glaciation. This is a model by Bob Burner. This is quite simple, but I think that this is quite a correct model. Okay, and now to that you go clearly, well, the installation of a huge ice sheets, ice cap, located on the map that I just showed you. Okay, so now one of the key points, I guess, for what will follow, this is probably during this time, especially during the Permian, but we start in the Carboniferous. This is a reptile evolution, and reptile evolution, that's to say the onset of the dinosaur. And here, this is just the evolution that you can see, showing more or less, well, that you have here two main part of evolution. The synapsid, which will give rise to the therapsid, and later in the Triassic to the mammals, which is quite important. And the other branch, this has a diapsid, which will give rise to a lot of reptiles. Some are marine, like ichthyosaur and plesiosaur, but a lot of them were dinosaurs, like the sauropods. And from the dinosaur branch, so the sauropod branch, you can get probably the birds, okay? So this Carboniferous time was a time of expansion of the first reptiles, especially on land, but also on sea, okay? And this is quite important, because just remember you that we are here by now. We are the mammals. And if you go back with the mammals, you go back to the Carboniferous origin, this synapsid. And the first real mammals are appearing after, at the end of the Triassic. We'll talk about that later on too. Okay, I will stop here and we'll start again at 2 o'clock. That's fine?